Hello everyone. In this paper, we will be talking about map generation from large-scale, high-quality remote sensing imageries. What are the challenges and how we try to address them? So, why are we still talking about map generation? Well, map seems so widely available and easily accessible everywhere. But as a matter of fact, there are still vast areas on Earth that are not mapped, mostly in the remote areas, but surprisingly sometimes in the very high-density city area as well. And as we experience every day, our city is constantly under construction, with new buildings being added and roads being rerouted all the time. It would be great to have an automated map generation process to take advantage of the high-resolution remote sensing imageries like satellite imageries and convert them into map in a more timely manner. In that way, we will have a more updated map that keeps tracking of our ever-changing planet. Furthermore, in the case of a disaster response, where existing infrastructure has been moved or destroyed, it is vital to provide updated map for the response team to prioritize their tasks and help with their rescue route planning. There has been some research work done in this area. Firstly, the SpaceNet hosts a series of computations, including 3 rounds of building detection and 2 rounds of road detection computation. It provides high-resolution satellite imageries from digital globe for 5 cities across the world, including Atlanta and Las Vegas in the United States, Paris in France, Shanghai in China, and Khartoum in Sudan. The winning solution of the building detection computation uses a UNet architecture. We want to point out that the data provided in SpaceNet is not freely available elsewhere except for the 5 cities, and we have observed that the huge variation in man-made infrastructure from one geolocation to another has resulted in the poor generalization performance of the trained model from one location to a new location. So we argue that we need to have more training data that covers more geographic areas in order to be able to generate map for the whole world. Another study is the cyclogram paper. The most famous example using cyclogram is changing horses to zebras and vice versa. Basically, cyclogram tries to enforce a one-to-one mapping between 2 distributions. Satellite image to map translation was an example used extensively in the paper, and it is shown that cyclogram performs better comparing with a few other GAN networks on the task of converting image to map. In our paper, we will utilize both the UNet and the cyclogram architecture, and we will explain them in detail. For any learning algorithm, we must first examine what are the available labeled data that we can use. With recent development in remote sensing, huge amount of aerial or satellite imageries are becoming publicly available. The counterpart for labels are building up too, for example, OpenStreetMap, which is a collaborative project with over 1 million registered users across the world, providing labeling of man-made infrastructure. Although it has been growing tremendously recently, it still bears significant inaccuracy when we examine closely. As you can see, the populated city areas are generally well labeled, with houses and roads matching closely to the images. However, when it comes to rural area, where the majority of the road map generated by non-military GPS signals are not well aligned, and in some suburban area, houses are not completely labeled as well. And even in some populated city areas, houses are not labeled at all. So with the status of OSM label being incomplete and inaccurate in some situations, can we still utilize it to train a model for map generation? Our approach to deal with the inaccuracy and the incompleteness of map generation can be summarized as feature-weighted cyclogram and incremental data augmentation, which we will explain in detail. The cyclogram network uses two sets of generator and discriminator networks, and the two sets of networks are connected by a cycle consistency loss, where the pixel-wise difference are computed between the input and the regenerated counterpart of the input through two generator networks. In this setting, the inaccuracy in OSM is now counted as a pixel level loss. Instead, a GAN loss is used, which is more tolerant in terms of map label inaccuracy. In our work, since we are really interested in the pixels representing houses and roads, we introduce one more loss called feature-weighted loss, which is like an attention mechanism where we add more weights on the difference from the pixels belonging to roads and houses. So how are feature pixels extracted? One nice feature about OpenStreetMap is that houses and roads are labeled with a fixed set of colors. Like houses are labeled with a sandy brownish color, and the roads can be white, yellow, orange, or blue based on their types. We then utilize a well-established color similarity measure to extract the pixels that are labeled as houses and the roads to generate a pixel-level mask. It is then used to generate the feature-weighted loss. About evaluation metrics, we have adopted similar evaluation metrics from the SpaceNet computation, which are a classification error metric of precision, recall, and F1 score. First, each house in the OSM map and the generated map are extracted from image using the color similarity measure described earlier. Then each individual blocks are converted into a polygon representing a house. Then for each house in the OSM, if there is a house in the generated map that has an intersection over unit greater than or equal to 0.3, then we count this OSM house as a true positive. False positive are the ones labeled in the generated map but no matching houses found in the OSM map. And the false negative ones are the ones in the OSM map but no matching label in the generated map. Then the corresponding precision, recall, and F1 can be computed according to the formula. As we pointed earlier, the OSM labels are not complete in terms of house labels, but it is observed that once a house is labeled, it's likely to be accurate. Then we focus our evaluation metric on recall, which is the percentage of OSM labeled houses correctly labeled by the model. First, we'd like to quantitatively show the level of completeness of the OpenStreetMap house labels by computing the house density across different cities in the same state and the SpaceNet city Las Vegas, which has the most complete house labels. Here, house density is defined as the number of houses per kilometer area. We extracted data for 4 cities in the state of Texas, Austin, Dallas, San Antonio, and Houston. We argue that since they are located in the same state with similar sizes, the house density for these 4 cities should be very close. However, as is shown in the table, the house density ranges from over 1,700 in Austin to less than 100 in San Antonio. Clearly, the house labels in San Antonio is very little and poses the biggest difficulty in terms of model training. Even for the city of Austin, its house density is less than 60% of the house density in Las Vegas, which also indicates there is certain level of incompleteness in Austin too. First, we want to see how cyclogram compares to the winning solution of UNet on accurately labeled dataset. As is shown in Table 2, UNet indeed generates much better F1 score compared to cyclogram on the accurately labeled dataset. We want to argue that the SpaceNet data for Vegas only contains house labels, no road labels are provided. As cyclogram is a translation model, it would not be a good idea to provide only one type of label, whereas a lot of other different landscapes are labeled as background. Then we want to see the model generalization power geographically. We use a model trained using Vegas dataset and to generate maps for the Austin testing dataset. As is shown, even with UNet, the recall score dropped from over 80% to only 25%, which is a significant drop, which supports our argument that there needs to be more geographically diverse training data set in order to generate map across the world. Next, we tested the feature-weighted cyclogram using the Austin dataset together with the base cyclogram and UNet, and the results are shown in Table 4. Feature-weighted cyclogram boosted the performance of the base cyclogram model and generates comparable recall score with the UNet on the Austin dataset. Then the next question is, which model generalized better in terms of geographic new locations? We then use both feature-weighted cyclogram and the UNet trained using Austin dataset and infer on the other three cities in Texas. As is shown in Table 4, feature-weighted cyclogram shows better generalization across all the other three testing cities. Now we introduce incremental data augmentation. As we have observed, the feature-weighted cyclogram shows better generalization performance from one city to another within the same state. We use cyclogram trained on Austin dataset to generate maps for the training dataset for all the 4 cities in Texas. We then add all the false positive house labels back to the OpenStreetMap to form a new training dataset, which we call augmented training dataset. As is shown in the examples, the first image is the original OpenStreetMap. The second is the augmented map. And for reference, we also plotted the corresponding aerial image. We believe that the augmented map are more complete in terms of house labels. We want to emphasize that all the testing data set remains the same. No data augmentation was performed on any of the testing data sets. In Table 6, we show that the house density has been significantly boosted in the augmented map for all of the 3 cities, even for Austin, of which the density is boosted from 1,723 to over 2,100. Now, as a result, the recall score from both the feature-weighted cyclogram model and the UNet model has been significantly improved. For example, the recall score of Austin using UNet is at almost 85%, which is close to that from the SpaceNet winning solution for Vegas, which is based on a more accurately labeled dataset. To provide a more complete evaluation, we performed a manual inspection on the true F1 score for the Austin dataset. We randomly sampled 100 testing data points, then manually counted the true values of the true positive count, false positive count, and false negative counts. And then we compute the true preseason recall and F1 score as summarized in the table shown. As is shown, the overall F1 score from both the feature-weighted cyclogram and the UNet are all above 80%, especially for UNet model, which achieved an F1 score of 87.5, which is comparable to the winning Las Vegas F1 score of 88% in the SpaceNet computation. Indeed, the combination of feature-weighted cyclogram and data augmentation has lifted the performance of the model trained on a less accurate and less complete dataset as good as that trained on a very accurately labeled dataset. Since scaling the mapping task to the contiguous of the United States calls for parallelization, we then adopted a distributed stochastic parallel gradient descent training scheme. In traditional parallel deep learning, one uses a central parameter server, which may suffer from straggler delay, where the overall training speed is subject to the slowest worker in the network. Then people proposed asynchronous parallel training. However, asynchronous training may suffer unstable convergence. We have implemented a decentralized training scheme where there is no central parameter server. The update of parameters are performed on a node-to-node basis. Furthermore, researchers demonstrated that Decentralized deep learning is guaranteed to have the same convergence rate as synchronous training. In our experiment, the computational workload is distributed onto a cluster of 16 GPUs, and we achieved a speedup of 14.7, which is very close to the ideal condition of linear speedup. We have made the generated map publicly accessible through a big data platform, Pairs. Pairs is a big data platform specifically designed for massive geospatial temporal data, such as maps, satellite images, weather forecast, drone images, IoT sensor data, and so on. Pairs is based on the scalable key value store of each base. For users, it takes care of various complexity in the geospatial domain, where, for example, hundreds of formats and geoprojection exists, provided by dozens of data sources. Pairs employs a uniform geoprojection across all datasets, with optimized key design that ensures efficient data storage and fast data retrieval. To retrieve the generated map features as color overlaid along with the aerial image in the background, we show the sample JSON load that can be used to query such data from Pairs. The figure on the right shows some additional example datasets hosted on Pairs as well, such as crop types across the US, Landsat satellite images, flood risk, and so on. You are very welcome to explore the datasets on Pairs. To conclude, geographic heterogeneity calls for more broadly openly available training datasets like OpenStreetMap, although there's inaccuracy and incompleteness in the OSM label. We have proposed the combination of feature-weighted cyclogram and incremental data augmentation, which has significantly improved model accuracy and generating compelling results. We're planning to further explore more advanced data augmentation schemes. And to scale out the model, we applied a decentralized parallel stochastic gradient descent algorithm, and we achieved a 14.7 speedup on a cluster of 16 GPUs. We will further experiment with asynchronous decentralized parallel stochastic gradient descent algorithm, which we believe will provide even higher speedup. Our final goal is to generate more accurate map across the US and make them available to the public. Finally, thank you very much